So thanks, all of this. So I don't know what they should done based on the time.
All right, I think that's everybody from the waiting room transferred in. Okay, welcome everybody to our first webinar of 2024. Today we have a really interesting topic that Dr. Sangao is going to tell us a little more about as the moderator for today, but I wanted to welcome you on behalf of UCGIS and remind you we do these periodically. There's not a set schedule, but we do them roughly monthly, and if you have suggestions for a topic, we're always open to that. You can always email me at arock@ucgis.org. And with that, I will welcome you and then turn you over to Dr. Sangao.
Yeah, thank you, Amy, and also welcome everyone. And I just actually saw a question about the recording. Yes, this webinar will be recorded, but will only be shared through the UCGS portal. So if your institution is a UCGS member, and you will be seeing the recording. Yeah, and with that, it's my great pleasure to introduce the speaker today. So Dr. Ziqi from the University of Florida State University, and he is currently assistant professor of quantitative geography. And before that, Ziqi actually was an honorary research fellow at the University of Glasgow at the UK. And before that, he got his PhD from the Arizona State University in the US. So Dr. Lee's work actually has been mainly focused on development of spatially explicit and interpretable machine learning statistical models. And he was one of the primary developer for several well-known models we know, such as multi-scale GWR and Python library, and joined with many others from the ASU team. So with that, I will turn my floor to Dr. Ziqi, and today he will be sharing a very exciting work about GeoShapley, especially putting my Geo AI hat. So that is how geospatial scientists can also contribute into the AI world. Thank you.
All right. Thank you, Dr. Gao, for the very kind introduction. I'll just start to share my screen. Right. Just before that, I would really like to thank Dr. Amy Rock for organizing this, and also very extensive promotion efforts from Dr. Gao and Dr. Ling Bian. They're really very hardworking in terms of promoting this webinar. So I'll just get this started. So today I'm going to talk about GeoShapley, which is largely based on this particular paper. So I put a QR code here if you want to scan it and read it later, or if you just search for GeoShapley, the paper should be able to pop up. Okay, so here's the outline for today. I'm going to talk about a little bit about the background, particularly on model explainability, and then I'll have hopefully like a gentle introduction to Shapley values and then GeoShapley values and some of the results from the paper. And then lastly, I'll talk about some practical considerations regarding using the method with the Python library. So there have been really exciting and extensive efforts in kind of the field of GeoAI, and these are just selected some really nice summaries or reviews or handbook that describe the state-of-art GeoAI models, methods, and applications. So I don't really want to go over how the development of GeoAI, but the one thing that I want to stress on is that there seems to be a common message from many of the review papers that model explainability and interpretability seems to be an area of research that is lagging behind in the GeoAI research. So, for example, I'm citing the Hus et al. 2024 paper from Annals of GIS, which is a reflection of the past 5 years of GeoAI. and which summarizes some panel some discussions from a panel at a previous AAG. So from all the panelists, the limited explainability of current GeoAI models seems to be one of the areas that has fallen short. I'm also citing the kind of the introductory chapter from Dr. Song's, Dr. Hu and Dr. Lee's handbook of GeoAI. And there seems to be some more work that we want to do in terms of to make GeoAI models more explainable. And in a very recent maybe commentary from Joseph, interpretability seems to be a very important pillar from the science of GeoAI. So model explainability and interpretability seems to be, the kind of the challenging part, and that's very true. I think it's actually very challenging because of the black box nature of AI. So not just GeoAI, but for AI machine learning, themselves. So this is due to the complexity of the model. So usually for AI machine learning, they involve a large amount of parameters. There might be lots of nonlinear transformations, ensembling, and all these mechanisms make the model to be very complex. And it's really hard for us to understand a machine learning model the same way that we understand more transparent, like linear regression or statistical models. So this kind of, people's opinion about AI to be a black box is actually pretty crucial. Might be one of the major criticisms of using AI is the lack of explainability. Right. So from a societal perspective, AI has really expanded into many critical domains, and such as health, emergency management, and so on and so forth, and most of which they actually involve a geospatial aspect. And without explainability, it's kind of hard to ensure the application of the model or the development of the model to be to be reliable, robust, transparent, and fair, and without bias. And from a scientific perspective, and especially, I'm kind of like a geographer, so many of the tasks in geography we're trying to seeking for spatial process understanding rather than making prediction. So making prediction is very important, but there's also arguably or equally important is to look at their processes underlying those spatial phenomena, spatial distribution of data. So this is kind of, understanding, process of extreme weather versus predicting extreme weather. So, so I'm currently in Florida. If you watch the news, you know that we're expecting a major hurricane, like Category 4 hurricane that's coming through actually directly at Florida State University campus. So, predicting is very important, but to know kind of the process will be also important. And to know the process will lead to better prediction. So recognizing the kind of the AI explainability gap that really emerges in the field, which is called explainable AI. I think the idea of explainable AI seems to be very broad. It really ranges from methodology all the way to like policy, etc. But here, what I want to just to emphasize with a very simple sort of definition is to have a set of processes or methods that allow us to better understand how machine learning algorithm, how AI works. Right. There are several objectives. Right. So we can improve our understanding. We can be more confident to use the model, to get a better understanding of the model parameters as well as the outcome, and to understand what it can do, it cannot do, and the uncertainty attached to the model, and also can help us to inform future model development. That's kind of the general several objectives of the kind of the idea of explainable AI. So I'll give you some examples of explainable AI in the application of spatial kind of spatial area, like geospatial domain. For example, I'm kind of citing the paper from Su and Lee published in IJGIS they applied a computer kind of explainable AI method to computer vision task. In this case, is like it's an object detection. So explainable AI can help us to understand which part of the image is driving the model to make a certain classification decision, right? Whether this is a volcano, whether this is some other land feature, and whether the kind of the features that the machine pick up match up with our human expectation, right? So we can get to see if the results are sensible from this XAI application. And here's another application for graph data. So graph neural network has been quite widely used in GeoAI or in geography. Here, Liu et al. The paper published in EPB. They used the GNN explainer trying to explain which subgraph or which node and also node features they play like a key role in predicting in explaining the prediction made by a graph neural network. And also for data such as the normal regression type of data, like a tabular data analysis. So usually people are interested in like feature importance. So which are the features, predictors, covariates that drive the model? And what are the kind of partial dependence, right? The relationship between a feature against the kind of the dependent variable or the label. Right? So here are some feature importance or partial dependence plot are quite widely used when interpreting tabular data. So next, I'm going to talk a little bit about how XAI works. I may guess some of our audience might be less familiar with some of the XAI methods. So in general, XAI method can be classified into two types. So the one is called model-based or like model-specific. The other one is called post-hoc or model-agnostic. So the model-based approach, for example, some of the intrinsically interpretable models like a linear regression, the coefficients and how the model is being estimated, they are linked together. So that will be considered as one of the model-based approach. But there are some other approach, for example, like some of the feature importance scores from decision tree-based models, some of the neural network-based models, they all can fall into this model-based approach. And the other approach is called post-hoc or model-agnostic. So this is the sense that we don't really need to look into the inner working, the inner mechanism of the machine learning model. Instead, we're looking at the input and the output. And we're trying to find some ways to probe this black box with some input and output. And based on the pair of input and output, we're trying to guess what's going on or approximate what's going on within the black box. So I'll give you, so much of the kind of the recent progress has been focusing on this post-hoc approach. And one of the reasons is because you can have a separate model-agnostic XAI method that can work with all different types of model, regardless of the model structure. So it can be really helpful for diagnosing different models that being trained on the same data set. So the entire GeoShapley work is actually on the second, the bottom part. So it's actually a post-hoc method and the model-agnostic method. I'll give you like a toy example to explain what does it mean by post-hoc. So you have a trained model, right? So the black box is just a trained machine learning model. And you give a set of input and it will have a set of output, right? Because we can give arbitrary input and the model will give arbitrary kind of output. And with enough experiments, in this particular example, if we pass a sequence of number 1, 2, 3, 4, if the output is 1, 4, 9, 16, with enough experiments, we should be able to have a guess. Not, we need more data points, but we can have a guess about the functional form that's been inside of the black box. So in this case, it's very likely to be like a quadratic function. We probably need some negative values to have higher confidence, but we can have like a general guess for what's going on within the black box. If we have multiple dimensions of the data, for example, if we have two columns, and your model output is largely based on one feature or one column, and it's not really dependent on the other feature. So we can sort of guess, make a guess that the first feature, the first variable, is more important than compared to the second variable. And then functional form and the variable importance seems to be the kind of the major task for for doing like traditional regression problems. However, there's a question. This way is still pretty crude, right? It's kind of a pretty naive way. Is there a more systematic and theoretically grounded way to probe the black box so that we can have like better understanding about the feature importance and the functional form within the machine learning model? So then I resort to this, the Shapley value idea from game theory. So Shapley value is, kind of developed from Dr. Lloyd Shapley, who actually won the Nobel Prize for this particular concept. So the original idea from game theory is trying to fairly distribute a total gain or like a total outcome among different players in cooperative games. So I've put the Shapley value formula here. For example, the Shapley value for a particular player in the game is actually, there are two parts. So the first part is a marginal contribution. So we're thinking about all the permutation of players. And then we look at the permutations with this player and without this player so that we can get a marginal contribution. And then we average over all possible permutations so that we can get like a weighted average of the marginal contribution. And that will be the Shapley value, like the kind of the fairly distributed value for that particular player. So if you find that still to be quite convoluted, I have a very simple example that is actually being presented in the paper. Consider there are some player sets, right? So we have ABC as 3 players in a cooperative game, and they deliver different gain or deliver different outcome. So what the Shapley value formula is doing is trying to iterate the possibility with a particular player and without the particular player, and then weighted by kind of the size of the player set, and then do a weighted average. So if you follow the formula from the previous slide, we'll be able to get the Shapley value for player A is 7.5, for B will be 20, and for C will be 120.5. So from this example, we sort of know player C is the most important player in this particular cooperative game. So to extend from game theory to machine learning, the first paper that introduced this idea is from the Strom-Belch and Kononenko paper in 2014. So they think about the players can be the features in machine learning, the game will be the model, and the gain, like the outcome, will be the model prediction. And Shapley value will provide a method to distribute the model prediction to the features in a very fair way. And the kind of the best part of Shapley value is because they have very strong theoretical grounds from game theory. And these are very useful properties when we actually try to leverage this method for a machine learning model. For example, the efficiency property refers to that we'll be able to break down the prediction into additive components. So the contribution from each feature will additively add up to the prediction plus a base value, which is like a baseline value. And such as the symmetry and the null player properties will refer to, if 2 features, they have the same marginal contribution over all possible permutations, they should have the same Shapley value. They should share the same importance. And if it's not contributing at all, it should have a 0 Shapley value. So these are kind of very important 3 properties. And there are some other properties which are more on the practical or interpretation side. For example, the unit of Shapley value will be the unit of y. So no matter if you are doing a classification problem, it can be probability. If you are modeling a percentage, it can be percentage. So if you're modeling like a count data, it can be in terms of counts. So the unit of Shapley value will be the unit of the thing that you're trying to model. And Shapley value will also have signs indicating direction of the contribution, and the magnitude of the Shapley value will measure the strength of the contribution. So I think these kind of three properties make Shapley value to be very different, or to be much better than the previous feature importance score, such as some of them from the decision tree based method based on gain, Gini coefficient or something like that. And there's another useful connection between Shapley value to like a linear regression. So for example, this is also actually presented in the paper. There's a strong connection of Shapley value against the additive model, that the Shapley value represents how each feature marginally contributes to the prediction. So actually, if you plot the partial dependence between feature against the Shapley value, you will show like a linear line, and the slope will equal to the prediction to the coefficient in the linear model. So Shapley value and linear systems there's a like very nice connection between each other, and we're sort of all familiar with linear regression. So Shapley value will have very nice connection to something that we are familiar with. And what really make Shapley value to be popular and widely applied is thanks to the a method which is called SHAP. So from this Lundberg and Lee paper in 2017, and also there's another paper for a particular tree-based method. So what SHAP is doing is developing a set of efficient estimation methods, because the original exact Shapley value, the calculation will be NP hard because we need to permutate different combinations of features. So, the SHAP package provides lots of great estimation methods, and also very user-friendly Python package with nice interoperability as well as visualization capability. And also, SHAP unifies some other explainable AI methods into the same Shapley value framework, so that can also be used for image, text, and tabular tasks, not just traditional regression tasks, but can also be used for image and text-based tasks. And SHAP is also kind of widely employed in the leading cloud AI platforms, including the ones from Google, IBM, Microsoft, Amazon, and its academic influence has also been quite substantial. So there'll be probably tens of thousands of papers published based on SHAP so far, including some of them are in top journals such as Nature and Science. And also in terms of GIS, recently I started to, probably in the past 3 to 4 years, I see that many papers have used SHAP, the concept of SHAP, the package, trying to explain machine learning models for many of the geospatial applications. So the last property that I want to stress on is on its local interpretation. So this is contrary to global interpretation. So in the way that global interpretation trying to explain overall model behavior, like what are the features that are overall important in the model, whereas local interpretation can provide better details that for each individual data points, so that you'll be able to understand how feature importance may vary across data points. And as a geographer, I sort of been a little bit sensitive about the kind of this idea of global versus local, right? So especially my entire dissertation has been on the local modeling approach. So that's why I was trying to link the local interpretation with approach such as local effect or spatial effect, in the sense that if the data points in your machine learning, if they are georeferenced, then can we leverage this local property in Shapley value to manifest the spatial effects captured from machine learning models, and if any, right? So previously we actually don't know, but whether machine learning models, they can adequately capture the spatial effects that we traditionally be modeled using spatial statistical models. So this kind of inspiration that I have, I did some experiment, and this work was before GeoShapley, which is considered as a premier kind of work before this, which was published in CEUS. what I did is I was using SHAP together with the extreme gradient boosting model, trying to explain using some simulated data, trying to explain the spatial effects by leveraging the interaction effects involving location coordinates. And surprisingly, actually, I was quite surprised that the results from extreme gradient boosting are really similar to the spatial statistical results from the models that used the multi-scale geographic weighted regression and the spatial lag model. Right? So from this paper, we're really trying to link the machine learning through the lens of explainable AI with the traditional spatial statistical models. And this comparison is really at the parameter level, not just at the overall model accuracy level or the overall feature importance level. However, there are some technical limitations that I sort of found from that particular exercise of SHAP. I refer to this like the off-the-shelf SHAP, so the one that you can, by directly using that SHAP package. First of all, the current implementation of SHAP is only available to explain interaction effects for tree-based models, such as decision trees, random forest. So we cannot use this approach for other model structures, such as neural networks, which have been, and deep learning neural networks, which have been very widely used in GeoAI, geospatial applications. And the second limitation is the coordinates of location are treated as two separate players instead of just a single joint player. And according to a kind of paper, joint Shapley value paper from Harris et al. In SCLR, they mentioned that there are some properties of Shapley values that will not be guaranteed when joint features they present. So this sort of the earlier work that make some motivation to develop a Shapley value kind of framework that will be specifically useful for geospatial data, for location data. And I put this like a little bit more formally, that GeoShapley conceptualize the location as a joint player in this game theory framework in the model prediction game. And by doing that, we'll be able to quantify the importance of location in the model and how location interacts or provides synergies to other features in the model. And more on the technical side, GeoShapley is estimated by extending the kernel SHAP method from the SHAP paper and also the joint Shapley value framework from the Harris paper. There are some more technical and mathematical details that I won't cover in the talk, but if you're interested in, you can read the paper. And at the end of the day, the GeoShapley will be a model-agnostic approach that can be applied thanks to the Shapley framework that can be applied to any. Here, any might be a little bit over-exaggerated, but sort of like most statistical and machine learning, like supervised machine learning models. So the major addition from going from Shapley to GeoShapley, so this is kind of the formula from the Shapley value. So each model prediction is broken down into two additive components, a base value, which will be like a global intercept in a linear regression model, and the contribution from individual feature to the prediction regardless of location, right? This is kind of like a aspatial effect. Usually will manifest like a nonlinear effect. So there will be two additional components attached to this new formula. So now each model prediction is broken down into 4 additive components. So we have a phi GEO, which this is a contribution from location to the prediction. Its interpretation is very similar to a spatial fixed effect from spatial econometric literature, or the idea of having a local intercept or the intrinsic contextual effect in a geographic weighted regression model. So some interpretation about local intercept, I believe last year, probably a similar time, Dr. Fotheringham gave another UCGIS talk to talk about the recent paper on measuring unmeasurable, which we illustrates the idea of intrinsic contextual effect from location to kind of the prediction or to the variable being modeled. And the other part that's highlighted in blue is this kind of like a joint contribution of location and feature J. So this will manifest a spatially varying effect. The idea here is that how a feature will affect the prediction will not only depending on the feature value, but also it will depend on the location of that particular observation. So I know I seem to be a little bit slow, so I'll try to go through everything. Here I'm going to talk about some results presented in the paper. So first, I validate the GeoShapley value using some ground truth data. So this is a case that we can define some true data generating process. And then the expectation is if we apply this GeoShapley value to a model which is 100% transparent, 100% true model, it should have 100% explanation accuracy. And then I'll demonstrate GeoShapley value when applied to models. Models will always approximate, the kind of the data. In that way, I'll demonstrate the based on synthetic data, but also on a simple house price model data set. So to validate GeoShapley, I come up with a simple additive data generating process, which involves a local intercept, 2 spatially varying effects, like spatially varying coefficients, and 1 global linear effect and 1 global nonlinear effect. It's like a U shape. So this is kind of very similar to many of the simulation work from the spatial statistical literature. And based on the true model, I give some arbitrary input. And because we have access to the true formula, the true data generating process, we'll be able to generate true outcome. And then I use GeoShapley, trying to explain based on the true outcome and the input, trying to explain what's going on with the true model. And the result here is I didn't just copy paste the same figure, but the explanations generated from GeoShapley are exactly the same as the processes that we define in the true model. And at the bottom here is there's a link. If you want to go to the code, you can find this validation. So this validation gives us some confidence in trying to validate the GeoShapley work for like the real data, right? The case that when we don't have access to the true model. So in 100% of the case, we don't have the true formula to describe the data generating process apart from like some physical laws. So in reality, we rely on a model to take the input and the output in the outcome to build a model and to generate a prediction. And if the prediction is kind of close enough to the real data, right? If you have very high accuracy, then you can use the GeoShapley method trying to explain this approximate model, the black box model, in the hope that we'll be able to shed some knowledge, help us to understand what's going on in the true model. So to follow this kind of the same framework with the same synthetic data set, I applied several statistical and machine learning models for that synthetic data set generated from the true model. You can see that the R-square value won't be, it's not perfect, right? Because first of all, there's a certain level of noise. Second, the model usually is just an approximate model. You won't achieve 100% accuracy. So then I applied GeoShapley to explain and cross-compare the 7 models, and the accuracy of these models can be seen from the table at the bottom in terms of the overall model accuracy. And these are the sort of the Shapley explained spatial and non-spatial effects across the models. On the top left corner, we have the true process, right? The one being designed, and the linear regression model, because it's a kind of a global method, it's either will be just a kind of a global coefficient or just like a linear coefficient, like a linear effect. Whereas for the random forest, extreme gradient boosting, the tree-based methods are able to capture some of the spatial and nonlinear effects, whereas the random forest is actually performing bad for this particular case. And on the right-hand side, actually, that will be the supported vector machine, Gaussian process, and neural network. They actually perform quite well for this particular data set. I mean, one of the reasons is that because the data generating process is still relatively straightforward, right? It's just based on a very simple function. So some of the, for example, neural network as universal approximator can really do that really well, can approximate the process really well. And the bottom one is the multi-scale geographic weighted regression. Again, it's a linear model, so it's not able to capture the U-shaped curve. And actually, you will actually create some bias to some other spatial effects in the multi-scale geographic weighted regression model. But with GeoShapley, you will be able to do this kind of cross comparison across different models. And then I'm gonna talk about the empirical example. I chose a very simple, probably not very exciting example on the house price modeling. And I chose the case studies because we sort of know that the location is important, right, in terms of deciding how or correlating with house price. And another motivation is this data also has been used in some recent spatial modeling papers, so that it provides a way that we can benchmark against the machine learning GeoShapley approach against some of the spatial statistical approaches. So the model that I have, which the dependent variable will be the log of the price, and then there'll be some attributes for the properties, bathrooms, square footage of living area, and then the last two variables are the coordinates of the property. I tried with different machine learning models, and this is a little bit different from the simulation study that extreme gradient boosting is actually the best performing model. It's not neural network in this case. And then I used GeoShapley to explain the trained XGBoost model. This is the first kind of the result or the output from GeoShapley. I borrowed the same visualization from the Shap package. So I call it like a Shap style summary. What this is doing is it will rank the importance of the feature from top to bottom. So the feature appears to be the top will be the most important feature. In this case, it will be the location, and comes down to some other attributes of the property. And the one with an X, or like the cross, are the interaction or the kind of the joint effects between location and other features. So they're considered, the kind of how age, in this case, age will appear to be relatively on the top. So how age and effects or correlated, probably correlation will be more a better word. With house price, it's not only depending on the age of the property, but also depending on the location of the property. And the GeoShapley value in this case is the percentage change in the property price. I did some reverse the logarithm transformation back to be a multiplicative model. So that would be like a percentage change to the property price. The second output from the GeoShapley kind of framework are the main effects. So these are the main effects that are aspatial. So they're kind of the global effect, regardless of location. So in the shape, most of them, they're shown as a nonlinear effect. Right? So most of them are shown as pretty nonlinear effect. For example, the square footage of living appears to be there's a the relationship will be sharp, and then it will flat out after a certain area of size of the square footage living. And so some of the other features like grade and view, they're actually defined by the surveyor. So they, the kind of people's perception on view or grade or condition will not be linear as what we expected. And you also notice there is some confidence band. I'll talk about the how do we measure the uncertainty, but the gray band will indicate a 95% confidence interval from the GeoShapley values from a bootstrap-based approach. And so we can also map the contribution from location, which will show us this map. So this is the map of the contribution of location to the predicted property price. The message here is location will serve as a multiplier to a base value, and the base value in this case for this data set is $430,000 for Seattle, kind of the average price for Seattle, the properties in the data set, and it will serve as a multiplier by 120% increase or minus 60% decrease relative to the base value, right? So this is actually not a very surprising pattern. So some of the well-thought neighborhoods are having the higher location value, whereas some of the more rural suburban areas have like fewer values compared to relative to the base value of the entire Seattle area. So we can also compare, for example, there's another study from one of my colleagues, Dr. Sachdeva, based on the same data set, but from a multi-scale geographic weighted regression model, and the right-hand side map is the local intercept of the MGWR. And we'll be able to observe the relatively same pattern. And actually, if you benchmark the actual value, it will be also very similar. But the data set is not exactly the same. So the model specification is also not the same. The color is a bit different, but kind of how the location will affect or is correlated with predicted house price are actually quite similar from the machine learning approach and also from the MGWR approach. And we can also benchmark against another model from Ansling and Emerald, which is based on spatial regime model that they split the data into 5 regimes based on a regionalization method. And we can look at for example, the age variable. This is the variable that has the strongest interaction with location. And you'll find that the two methods actually agree that in some of the central Seattle, the west Seattle areas, age will actually have a positive effect for house price. So older houses will actually be more expensive compared to newer houses. So there are a whole bunch of reasons. I explained that in the paper. Some of them, first of all, they're really in nice locations, neighborhoods. Second, they have some historical characteristics attached to the house. So some people that actually prefer some of the historical houses. And also some of the houses, even though they are old in age, but they are being recently renovated. But the renovation date is kind of not captured by the model. Right, so I'll probably spend another 5 minutes. So I'll talk about the GeoShapley Python package that you can use for your model, and you can easily install this from pip, or if you want to install the latest version from GitHub, you can also do that. And this is just a very simple example on the GitHub site, the front page. The key part is you want to specify a background data set. I have another slide to explain what is background data set. And then you just need to put a prediction function. And then you can use the GeoShapley explainer to explain your model. So some practical considerations. So first is the background data set. No matter in Shap or GeoShapley, there will be a background data set. So Shap and Shapley values are kind of relative. They are relative against a baseline, and the baseline value will be computed from the background data set. So there are several choices. You can use the entire training data set. If you have, if your data is not that huge, you can also use a random sample of the data set, say 100. Or you can use a representative sample point if you believe there's like a sample you want to benchmark against all the other points. Or you can use a set of representative samples from k-means or k-medians. And in terms of computation, the current implementation is a little bit slow. So even though with parallel computation, it actually scales quite well in terms of the number of data points, but it doesn't scale really well in terms if you have more features. Because there's still like some permutation involved. So some priority feature selection will be very helpful. And computation is also linked with models' prediction inference speed. So one way is you can have a relatively smaller size of the model and also choose a model with higher inference speed, like quicker inference speed. And future work will definitely try to optimize the computation demand. And uncertainties. So this is something that I want to highlight. Most of the post hoc XAI methods, they describe model behavior. They don't describe the data generating process, right? They only reflect what's being modeled by the model. They're not true to the data. The model training, there should be, if we use GeoShapley and the other XAI methods to explain, we should put enough efforts trying to make our model as accurate as possible. If you can't really, have a very highly accurate model, I always suggest you do a bootstrap so that you'll be able to quantify the uncertainty of the model to the data you have. The GeoShapley value is actually a deterministic method. It doesn't have lots of uncertainty. The only uncertainty comes from the background data set. But you'll be able to capture the uncertainties from the machine learning model using a bootstrap approach, right? So essentially you generate some bootstrap samples, you train the model, and then repeat that for M for enough times so that you'll be able to get a distribution of GeoShapley value. And these are the ones I used in the paper that you can get like a confidence interval and shaded band and so on and so forth. And the other practical consideration, so in some of the cases, we want to know like the spatial varying coefficient. This is probably because we have we're kind of familiar with the GWR framework that we only want to know the local coefficients. So there's two approaches currently supported by GeoShapley package. So one is a raw. So the GeoShapley, they're not coefficients. They're kind of the partial dependence, partial contribution, but they're not directly the coefficients from like a regression model. You can either do raw, or you can use a GWR to smooth the partial relationship, so that you can regress the essentially the top part against the bottom part for the raw method. The raw method will work well if the model has smooth decision boundary at the average value of your feature, but otherwise GWR will be an alternative. And there are also like a very kind of simple note, if you want to specify to be true, if you want to add the spatial primary effect when you manifest that spatially variant coefficient. So I think I have two more slides. The last practical consideration is interoperability. So GeoShapley is a model-agnostic approach. So it can directly support most of the prediction functions from scikit-learn, from XGBoost, TabNet, and so on and so forth. As long as you pass your data in a tabular format, and then you have a trained model, and then your prediction function will generate with one column for your testing data set for the data. If your data follows some other structure, you can actually also use GeoShapley, but you need to write like a wrapper function to describe how your model will do the inference based on the coordinates and the normal features. For example, I know many of the GeoAI models will have location encoding or some spatial embedding, and that part can be fall into that red box, and then the modeling will be the green box. But in overall, the entire black box here I have in blue, if you want to apply GeoShapley, you have to write like a separate prediction function, and then you can use this prediction function to together with the GeoShapley explainer. So lastly, I just want to summarize the contribution. First of all, GeoShapley provides a model-agnostic approach to measure spatially varying effects and nonlinear effects from machine learning models. We'll try to sort of answer the call that we need to focus on the explainability and the interpretability of GeoAI models. I don't think the GeoShapley will be I hope it will kind of marginally contribute to that area, but there should be more methods developed to enhance the interpretability for GeoAI models. Several future directions directly on top of GeoShapley. Formal uncertainty quantification is kind of important if we want to capture the uncertainty from the model, and computational improvements, causal capability, and integration with other GeoAI tasks. For example, for image-related tasks, technically it's possible because each pixel is indexed by a particular location. So it's possible, but some work might be needed to have a integration with that. All right, thank you for all of your attention. I know I'm a little bit slow. I probably spend more like 5 more minutes to talk, but I hope to have some questions if you have any.
Yeah, thank you, Ziqi, very much. Yeah, this is a great presentation. Also, thank you for your contribution to the expandable, machine learning community, especially who are interested in exploring the spatial effects using various geospatial data set. Yeah, so we actually have a set of questions, very interesting question already. So you can actually see them in the question answering. And for the audience, you can continue typing your questions in the QA box on your Zoom. If you like, you can also raise your hand, but I will, let Dr. Li to answer the question following the order. So the first question, I think, is from Dr. Huang Xiao from Emory University, and he actually asked in another way on the third question. So you can maybe start from that. Yeah, the question I can read quickly, and then you can prepare your answer. The question is, when incorporating the location coordinates and what are the embeddings into a machine learning model or deep learning model, how should we interpret their contribution? So considering that those purely like positional location encoding are not inherently expected to influence the results unless they are undressed spatial factors. So this is actually relevant to later. I think Dr. Guntram might also ask relevant question about the location and how those location encoding and be a joint feature in the GeoShapley. And I see several relevant questions about this. So especially the location coordinates and location encoders, and then those variables have spatial effects.
Sure. Yeah, thanks Xiao and Gongchen for the question. This is actually more from my point of view, it's like a philosophical question that in fact there are spatial confounders that we are never be able to account for. So that's kind of the reason that part of the reason that we observe some of the spatial effects is we're not be able to measure and quantify everything that the entire process that generates spatial phenomena. So the kind of the discussion that we had about we're trying to measure the things that are relatively unmeasurable. So I hope this is helpful. But if in the ideal world that we have formula for all of the decisions that we make for all of the physical phenomenon, then there will be no spatial confounders, and everything can be represented by deterministic formulas. Right? The other thing is, I think it might be possible for some of the physical applications, but in terms of social applications, it will never be hard to account for all the factors that people make decisions. So so there will be like some spatial effects anyway.
Yeah. So thank you, Ziqi.
Yeah, so in terms of Gongchen's question, so essentially I treat location either 2-dimension or multiple dimension as a single player. When they do the permutation, they will just appear simultaneously instead of appear in the permutation separately. So they're like a set, like they'll be like a set. They will join at the same time instead of separately when calculating the Shapley value.
Okay, yeah, thank you, Ziqi. And the next question is from Tian Ye. So this is actually about how to quantify the joint effects of predictors such as age versus location on your model, and the person also mentioned about the previous methods such as geodetector. So maybe is your method different from those existing methods?
Sure. So right, so I can explain the first part. So the joint effect is, so we kind of, you know, we use the model to explain a kind of like a permutated data or like a fake data without age and without the location, and then to generate a prediction. And then we use the model with another fake data, but with location, but without location, with age, but without location, and also with location, but without the age. And then we try to do that difference. And then so you can isolate how age itself affects the model prediction, how location itself affects the model prediction, and how age and the location together will affect the model prediction. So that's part I just borrow from the kind of the Shapley value framework. So in terms of comparison, again, geodetector, to be honest, I don't know too much about geodetector, but my limited interpretation is this is still following like a regression framework, but geodetector is trying to use the heterogeneity of the patterns, like the kind of levels, and then make associations based on the data. And the results from geodetector, they're not very measurable. There are some statistical tests, but they're not will be in the same kind of unit, or they cannot be interpreted as like a coefficients in a regression model setup.
Yeah, thank you, Ziqi. The next 2 or 3 questions I think are all relevant, and I can summarize as, you know, it's more about maybe when people will use your GeoShapley versus using the, you know, the popular non-aspatial Shapley, you know, method, and especially for not only spatial data but also for maybe time series and spatial temporal. So from Sana, Kejing, and another anonymous attendee. Yeah.
Right. So I think the one difference is using the normal SHAP framework, we are not be, well, from the CUS paper that we can, but you know, normally what I see for the most SHAP applications so far in the literatures, they don't really consider spatial effects. They only consider more for the on the nonlinear side, but not the spatial effect, like spatially variant effect and so on and so forth. But from GeoShapley, you'll be able to kind of, you know, to measure that with GeoShapley. And also the other thing is, you know, the normal SHAP you cannot run that on top of, especially for the interaction effect, you cannot run on top of like neural network models. So you can only do for tree-based methods. If the interest is on interaction effect, and also in some of the like the reason for I use joint Shapley is that some of the properties in the Shapley will not be available if you use the standard SHAP. Though the results might be very similar in some sense, but you know, on the theoretical property side, they will be a little bit different. And in terms of the time dimension, yes, so that's very interesting. And I haven't done any work for that. And I'm aware of work, for example, like time SHAP, which seems to be something that I am aware of. And for temporal data, to sort of to consider the joint feature between time and location would be something feasible, I think, but there might be some nuances because the temporal dependence is something that we want to take account for.
Yeah, great. Yeah, thank you, Ziqi, very much. We have definitely more questions, but due to the time limits, so we schedule for the 1-hour webinar. So I will copy all the questions, and you know, for the questions we didn't answer live, I highly encourage you to also maybe email Ziqi and to, you know, to your further discussions. And with that, let's thank you, the speaker, Dr. Ziqi Li again. Yeah, this is definitely a very enlightening work. Yeah, thank you.
Yeah, thank you, Dr. Gao, for moderating the talk. Yeah, thanks everyone.
For future UCGS webinar series. Thank you. Bye-bye.
Thank you. Stay safe if you're in the Southeast region.
Yes.